All right, here's our lesson on square root functions. This lesson and the next are going to be very similar. We're just starting with a different function to begin with. So the first biggest thing that you need to know is that square root functions are the inverse of quadratic functions. So remember that inverse switches x and y, and quadratic function means we're going to have this x squared here. So if I give us just some basic values to start with, x and y, let's just do some easy ones, -2, -1, 0, 1, and 2. So if I square -1, and I can actually go all the way to 3. I'm sorry, not -1, -2 squared, so I'm looking right here, -2 squared is going to give me +4. -1 squared gives me 1, 0, 1, 4, and 9. You should know all of those, so what you should probably do is take a moment to go ahead and plot that on your graph. All right, and now I know when I find the inverse, what should happen is that my x's and y's should switch, and it should be like a nice little reflection across this diagonal line, which is why we worked on inverses before we did this lesson. All right, so when I switch my x and y, my points are going to become 4, -2, 1, -1, 0, 0, 1, 1, 4, 2, and 9, and 3. Now there's actually a few points here that aren't going to work. And that is these first 2 points that I actually have here. Because if you take the square root of 4, you don't get -2, you get +2. You take the square root of 1, you don't get -1, you get +1. So these first 2 points aren't actually there. So we're going to go ahead and graph then. 0, 0, 1, 1, 4, 2, and 9, 3. Now notice that it doesn't work perfectly because we're missing part of the graph, but parts of this graph do reflect each other pretty well. So hopefully you notice that from the original function, and then for our inverse function here, they mirror each other across that line. So the last thing that we need to take a note of is just a comment about domain and range. All right, so for our original function, and remember an original function is called a parent function. And so for our quadratic parent, we're going to have domain is all real numbers, and range is going to be y is greater than or equal to 0. And that's because this lowest y value is 0 right here in the middle of the graph. For our radical function, or our square root function, my domain is not all real numbers anymore because I couldn't pick negative values, right? Because we can't take square roots of negative numbers. So that's going to mean x has to be greater than or equal to 0. And also the same idea for my y. When we do root functions, our y's cannot be negative either. So that's going to be y is greater than or equal to 0. Because the only place that this graph exists is where everything is positive. So what we're going to do is use some transformations and just review those on how to graph these functions, because they're going to start looking pretty complicated, but they're really not too tricky. All right, so this first page of notes that I just want to show you is what happens when we have translations. So remember, a translation, and this will help you for geometry too, because you're going to hear a lot about translations next year. Translations just shift things or slide them left, right, up, or down. So my first graph that they've given us here is the parent function. That's the one we just graphed. I've got my original points 0, 0, let's see, 1, 1, 4, 2, and 9, 3. And they are just telling me that my parent function looks like this. I've got a domain, x is greater than or equal to 0, and a range, y is greater than or equal to 0. What I want you to see is what happens when they start putting something on the inside. So remember our dance moves, right? That inside, we shake our head side to side, and we have to think opposite. So inside moves us left or right, and we want to do the opposite. So -1, in fact, means to go right 1. So notice that every single point in this graph just got pushed to the right 1. Notice that instead of being at 1, 1, it's at 2, 1. Instead of being at 4, 2, I'm at 5, 2. Okay? Notice also what that does to the domain and range. So the range stays the same, but since x is what was affected, the x changes from 0 to being 1. Kind of like it did when we changed the vertex in quadratics. Very similarly, we're going to see some changes if we put a number on the outside. So remember, in our dance moves, inside is opposite, but outside we nod our head up and down, and we tell ourselves it's the same, and that we are going to move up or down. So plus 2, in fact, means to do up 2. So in this one, we're doing two things. We're going right 1 and up 2. So they took this original point that was at 0, 0, and they moved it to the right 1 and up 2. And then they took the original point that was at 1, 1, and they moved it to the right 1 and up 2. The same thing with the point that was originally at 4, 2. It moved to the right 1 and up 2. All right, so the whole graph itself just kind of shifted there. Again, notice what that does to the domain. So right changes the value for the x, because right is an x direction, and up 2 changes the value for the y, because up is a y direction. All right, so those are our translations. You probably need to have these in your notes, but then we'll try some of these tomorrow. Okay, so this next slide is just a little tricky. We're talking about vertical changes to slope. And remember, slope for all of this is kind of in quotations, right? We're using that as kind of a loose word there. So notice in the middle here, this middle function in black is our parent function. And that's what everything is based off of, is the parent function, which remember is just the most simplest version of the graph itself. So what we want to do here is look at what changes happen. So if you have a 2 on the outside as your slope, you should notice that what that is doing is making the graph taller. And we call this a vertical stretch. All right, if you think about that, it's like it's being stretched upward, right? Like somebody is holding on, maybe like there's a handle up here and somebody is pulling this graph upward because that's a vertical direction. So where the 2 comes in is if you think about the vertical value, so this is a little weird, this red point is 0, 0. So when I vertically stretch that by 2, I'm going to change the y value times 2. Well, that just stays at 0, 0. My next point is 1, 1, and when I change its y value, it becomes 2, 1. Or I'm sorry, 1, 2. I said that backwards. 1, 2. Notice that the y value changed. On the green point, I started at 4, 2, but when I times by 2, I get to 4, 4. You see how the y values are the ones that are changing every time? And then our last point is at 9, 3. So when I stretch vertically, it's this last value that's going to change. And since it's times 2, that's going to become a 6. Right? See how that matches? The y value now matches with 6 instead of 3. Okay, if I had done, let's see, the other one that they give us here, this 1/2, is what we are going to call a vertical compression. And hopefully you've heard the word compression in some way before. Compression just means to press something down. So instead of having that handle that you pulled the function up, now we're going to push the function down. So this original point in red that was at 0, 0, now it's going to still stay at 0, 0, but my orange point, instead of being up at 1, it's only going to be at 1/2. That's at 1, 1/2. This green point, instead of being at 2, is pushed down to 1 because I'm cutting it in half. So now that's at, let's see, 4, 1. And then my blue point, instead of being at 3, we're going to cut that in half, and it's going to be at 1/2, or 1.5 rather. So notice that when you do this, because it's vertical, it's the y value that changes, which you should probably put in a point to yourself. Whole numbers stretch things and make them taller. fractions shrink things or press them down and make them shorter or smaller. And all of this is done with multiplication and division. The only other thing that I want to show you, and you already know this, is what do you think would happen if it said y equals negative 3 squared of x? So let's look at that on the next slide. Okay, so on these, the negative, like you know before, the negative is going to reflect it or flip it down, and the 3 is going to stretch it. So I just want to show you one so that you kind of get the idea of what the difference is between 2 and 3. So this original point is at 0, 0, this very first one. I think about if I want to flip that and multiply it by 3. So remember, I'm just doing the y value. That's going to change it to 0, 0, which isn't actually a change. All right, my next point, original point, is at 1, 1. And if I want to change that, I'm going to change my y value. That's going to change it to 1, negative 3. Right, I'm multiplying by what this value is out here. Okay, if I change my next point, that's going to be my original point is at 4, 2. So my new point is going to be at 1, negative 6. Sorry, 4, negative 6. Goodness gracious. All right, notice that it's just the y values that are changing every time. And then my last point out here is at 9, 3. So when I change just the y value, it's going to be at 9, negative 9. So let's see exactly what that looks like, because we know negative should reflect or flip the image down, and the 3 should stretch it so that it seems like it's taller or wider. All right, so my first one's going to stay at 0, 0. My next one's going to be at 1, negative 3. My green point is going to be at 4, negative 6. And my last point here in purple is going to be at 9, negative 9. So notice now, it's almost hard to, kind of tricky to see this, but now we've got this parabola that's like well, it's not even a parabola, right? It's just the function that's way stretched out than it used to be. Hopefully that makes a little bit of sense of how to do stretches and compressions. Come tomorrow and we're going to work through a whole bunch of examples just so that you feel a little bit more comfortable with how these work.